Hello, hello, and welcome to one of my favorite lessons in all of calculus. I'm super excited because this is just really cool. But I'm also a little bit nervous because, it's not easy stuff, and I so just want to represent it well and do it justice. So let's dive in and see what we have. Today we are learning Taylor polynomials. Take a moment, if you would please, pause the video and find the third derivative of both sine of x squared and then this huge polynomial here and see what you get. Now, if you took the derivative of sine x squared, you probably saw quickly that it gets complicated, right? So the derivative of sine is cosine, and then we keep the inside the same, and then we have to multiply times the derivative of the inside, which is 2x. So that is the first derivative. Now, the second derivative is going to be some combination of product rule and chain rule. And then the third derivative becomes that just again and again and again. It just gets complicated really fast. But hopefully you got something that looks like this, negative 8x cubed cosine x squared minus 12x sine x squared. Now b, this polynomial here, that's way easier, right, to take the derivative of because it's just a series of power rules. So we can do power rule 3 times. And you end up with negative 20x cubed plus 6x to the 7th minus 13 over 30x to the 11th. Now, what if I told you that this function right here and this function right here are, well, almost identical? Which one would you pick to work with? I would pick to work with the polynomial. You know why? Because polynomials are just easier to work with. Well, what's a polynomial? Polynomial looks like this. You have a constant and then a variable. That's a first degree polynomial. Second degree polynomial, you have constant and variable, and then you add a new constant and the variable squared. And you could just keep going, create bigger polynomials. You have the same constant, the variable, a new constant, variable squared, another new constant, variable cubed, and so on. So the question is, how do you make sine of x squared into a polynomial with Taylor polynomials? You ready for this? We're going to start off taking e to the x. That's a pretty simple one. We're going to take e to the x and turn it into a third degree polynomial approximation. So first of all, we're going to name our polynomial p of x. And e to the x at 0 is 1, right? So our polynomial should have the same property, that at 0, the polynomial equals 1. Now, if we want the graphs to have a similar shape near x equals 0, then they would have to have the same slope at x equals 0, right? Well, slope is code for derivative. So my f prime of 0 would have to equal my p prime of 0. We're going to be taking a bunch of derivatives here, so this is why we're starting with e to the x. If you have e to the x, the first derivative is e to the x. Second derivative is e to the x. Third derivative is e to the x. These are all going to come in handy. Now, back to the problem over here. My first derivative at 0 has to equal e to the 0, and that equals 1. That means my polynomial, the first derivative at 0, has to equal 1. So look what I have. I have a slope, and I have a point. So I can use point-slope form to find my tangent line. You've done this before. The tangent line is actually a first order polynomial approximation. Now we're going to keep going because we don't want to just stop at a first order approximation. If we want the graphs to have a similar shape near x equals 0, then not only would they need the same slope, they really should have the same concavity also. Well, concavity is found in the second derivative. So I need the double derivative at 0 of my function to be equal to the double derivative at 0 of my polynomial. Well, the double derivative of 0 of my function is e to the 0, okay, which is 1, which means the double derivative of my polynomial at 0 also has to be 1. Now, I started with the tangent line, okay? And in order to get a second degree polynomial, I need to add to that a new term with a new constant and an x squared. So there, I have a polynomial. Now, I need to get to the second derivative of that polynomial. Okay, so let's take the derivative. The first derivative would be, let's see, that 1 goes away. We've got 1 plus 2 comes forward, 2 times whatever constant is there times just x. Awesome. Now I'll take the second derivative. And I get 1 times 2, just the constant. Now I know that my second derivative at 0 has to equal 1. So let's just set that equal to 1. And doing that, we can solve for the constant. It's 1/2. That's awesome. So let's take that 1/2 and plug it back in for where the constant was to begin with. And there we have a second degree Taylor polynomial, or a second order polynomial approximation. Now look up here, let's graph it and see what that looks like. Hey, so cool. We started with the tangent line, now we have a parabola, and it's getting closer and closer to the actual form of e to the x. Well, so let's keep going. We can continue this process for the third order approximation. So for the third order approximation, my third derivative of the function would have to equal the third derivative of my polynomial. So again, at 0, the third derivative of e is 1, which means my polynomial, the third derivative at 0, also has to equal 1. So let's create a third order polynomial. We have the second order polynomial. We just have to add on the next term. So we have a new constant and x to the third, and we need to figure out the third derivative of that to set it equal to 1. So we'll take the first derivative, and we'll take the second derivative, and we'll take the third derivative, and we'll set that equal to 1 and solve for our second constant, which would be 1/6. And we'll just plug that back in, and there we have another polynomial, a third degree polynomial. So if we graph that, that is so cool. It just hugs e to the x. Only for a little while, but still for a little while. So let's take an overview real quick of what just happened. We started with the tangent line. Then we added an x squared term and found the constant to go with that. We had a new polynomial, and we wanted a third degree approximation. So I added an x to the third term, and we solved for the constant of that one. Okay, now look carefully with me for a moment. Just in front of our constant of the second derivative is 1 times 2. Just in front of the constant of my third derivative is 1 times 2 times 3. Because the repeated power rule creates a factorial. So this was the polynomial that I had originally come up with. But these constants, 1/2 and 1/6, I could rewrite them with factorials. I could say 1 plus x plus 1/2 factorial, same thing, plus 1 over 3 factorial, which is the same thing as 1 over 6. So I see a pattern developing. Do you see it? I could even go backwards and put x over 1 factorial, which is just 1. So if you had to guess the next term, what do you think it would be? Maybe 1 over 4 factorial x to the 4th. And that is the next term. Isn't that cool? So we could keep going on that forever and find a really close approximation. Now, before I move on to the next slide, take a deep breath, because what you're about to see looks scary, but we've literally just done it. This is the formula for an nth Taylor polynomial. And like I said, we've already done this. We've got our f of c. That was the point that they both share. And then we have like our little tangent line there. And then we have our second derivative over 2 factorial, our variable with a power of 2, our third derivative over a 3 factorial, a variable with a power of 3, and so on and so forth. Look at the end. We've got an nth derivative over n factorial and a variable with a power of n. Now, where did all these c's come from? This minus c here, that's just moving the graph to the left or right. So we'll deal with that in a little bit. You may also see a simplified version of this, where notice the x minus c's are all the same, but these constants, where did those come from? Those were just this part right here, the derivative divided by the factorial. So probably this doesn't make any sense yet, but stick with me because we're going to practice this a couple times. Now, there's a special kind of Taylor polynomial called a Maclaurin polynomial, and that's actually what we just did with the e to the x function. A Maclaurin polynomial is a Taylor polynomial. It's just centered at 0. So instead of all that x minus c that we saw before, there's just an x there. And that's because basically we're doing x minus 0 to the n, which is just x to the n. So really, you only have to memorize or learn how to work with this general polynomial, because the Maclaurin one just makes the c 0. So let's learn how to work with it. Okay, before we did e to the x, now we're going to do e to the 2x. So a little bit different. And then we're going to see how that actually compares to the actual function. Now let's set this up. We're doing a third order Maclaurin polynomial. So we need an x to the third somewhere in there. So we'll say our p of x is going to be approximately equal to, and it should have the same beginning point, f of 0. This is a Maclaurin polynomial, so it's all centered around 0. And then we'll add the first derivative at 0 times x, and then the second derivative at 0 times x squared over 2 factorial. And then we'll add to that the third derivative at 0, x to the third over 3 factorial. So that's what this is saying. That's just telling you how to build the general polynomial. So let me clean that up. Now, literally, the only thing we have to do is figure out the various derivatives at 0. So the function we're working with is e to the 2x. So let's just start by taking the derivative of that 3 times. So we've got e to the 2x, 2e to the 2x, 4e to the 2x, and 8e to the 2x. And we need each of those evaluated at 0, which gives us 1, 2, 4, and 8. Now we're almost done, because the 1, see, we just plug it in for f of 0. The 2, we plug it in for f prime of 0. The 4, we plug it in for f double prime of 0. And the 8, you guessed it, f triple prime of 0. And there we go. That's our Maclaurin polynomial. Now again, sometimes they will go ahead and simplify this. So 4 over 2 factorial is 4 divided by 2. That's just 2. 8 over 3 factorial is 8 over 6. So you might see it written like this too. Now, how accurate is that? Well, let's see. That's our polynomial. Now, f of 0.2 is 1.4918. Our p of 0.2 is 1.4906. Hey, that's pretty close. Let's try another one. We'll do the natural log. Okay, so we're going to try to turn the natural log into a polynomial approximation. We'll start with setting up something to fill in. So we're doing a 4th degree Taylor polynomial this time. Again, if you can start out by writing this stuff down, you're going to be golden. So the polynomial is approximately equal to, we've got f of, okay, now this one is centered at x equals 1. So we're going to have f of 1 instead of f of 0. And then we'll add to that f prime of 1. And then instead of just times x like we did before, we'll go times x minus 1. And then we'll add to that f double prime of 1 times x minus 1 squared. Notice the derivative matches the power over 2 factorial plus the third derivative at 1 times x minus 1 cubed over 3 factorial, and I'm out of room. We still would have to do the 4th one, but there we go. Now we just have to fill in these derivative pieces at 1. So we'll take ln of x and take the derivative 4 times. And then we can plug in 1 to each of those because that's what we're curious about. And now we just plug all those numbers in. 0 goes to f of 1. 1 goes to f prime of 1. Done. If we want to clean it up a little bit more, it could look like that. How close did we get on this one? Well, the natural log of 1.1 is 0.09531101. My polynomial evaluated at 1.1 is 0.095303. Look at that. To 4 decimal places, it's accurate. And we only have a 4th degree Taylor polynomial. What would happen if we went to infinity? Interesting question. We'll answer that in another lesson. Now, we've already kind of discussed this, the coefficients of a Taylor polynomial. There's this huge big thing that we've been learning about that's actually not that bad. And the coefficient of the nth degree term in a Taylor polynomial is just these parts here. The nth derivative at c over n factorial. So that's what I told you. When we clean it up a little bit, you might get coefficients that look a little bit different. But this is what they equal. The nth derivative at c over n factorial. So we can use that information now to answer this question. Let f be a function with a third derivative of. So they're just telling us the third derivative. 8x plus 2 to the 3 halves. What is the coefficient of x minus 2 to the 4th in the 4th order Taylor polynomial for f centered at x equals 2? Oh, that seems like a lot, but it's actually not that bad because what are we looking for? Well, that 4th term is going to be the 4th derivative at 2, right? And then x minus 2 to the 4th over 4 factorial. Okay. If we have the third derivative, we can find the 4th derivative. Clean that up a bit. And we need the 4th derivative at 2, so we'll plug in 2. And we get 12 over 18. So we've got this part is 12 over 18. Not 12 over 18, sorry, 12 root 18. So we've got this part, 12 root 18. And that's just over 4 factorial. Let me clean it up. And so 12 root 18 over 4 factorial is just 1/2 root 18. That's the coefficient. I love this one. This one's so cool because it pulls it all together. This I found on an AP Daily video. They have awesome videos on AP Classroom. So go check those out. A portion of the graph of f, along with the line tangent to the f at x equals 2, is shown in the figure below. The region bounded by the graph of f and the x-axis between 2 and 5 is shaded in the figure. Let h of x equal the antiderivative from 5 to x of f of t dt. Find the second degree Taylor polynomial for h of x centered at x equals 2. Oh my gosh, what the heck? So let's start by setting it up just the way we have before. Our polynomial is going to be, approximately equal to, it'll share the same point as h of 2, and then we need the same first derivative at 2, x minus 2, and then the same second derivative at 2, and that'll be x minus 2 squared over 2 factorial, and that's all we need because we're doing a second degree Taylor polynomial. Now all we have to fill in is these derivatives. So h of 2, h prime of 2, and h double prime of 2. So there it is, all nice and pretty. Now what is h of 2? Well, h of 2, we have to plug in a 2 for the x there. So we're going from 5 to 2. Well, that's upside down. So it's going to be the negative antiderivative from 2 to 5. And if you look in the graph here, they told us what it is. So h of 2 is negative 67 over 8. Okay, what's h prime of 2? I'm just looking at my polynomial here and realizing that I put 1s in there. Let's switch those to 2s. 2. I don't think I have a purple pen. 2. Okay. Now, what is h prime of 2? Well, h prime of 2, here's their tangent line. H prime of 2 is right there. It's 3. The last thing we need to do is figure out h double prime of 2. Well, that's going to be the slope of the tangent line, which is 1. And we have everything we need to plug in to our polynomial. I just think it's so cool how Taylor polynomials work. And we're going to be doing a lot more with them. So make sure you practice this a while first before moving on so you can feel real comfortable with where to come up with them. Okay, see you next time.